Hello and welcome back to the Advanced Malware Analysis course. In this part of the course we're going to be looking at automating analysis when it comes to loaders. So without too much explanation, let's just get started. So this is following on from the last episode, so if you haven't seen that I'd recommend going and watching it because we actually reverse engineer the loaders that we're going to be looking at automating analysis for in this part, so it will be quite helpful. But anyway, so before emulating the communications of a sample, we need a way to get the latest command and control servers as well as encryption keys from the payload. So we want to do this automatically, as debugging the sample in a VM takes quite a long time and extracting it manually also takes quite a long time. And we also want to do it on our own machine. Sandboxes also take quite a long time as they aren't really focused on the configuration but more on the behavior, although you can get certain sites that focus on extracting configs like Cape. So an example of this is Dridex loaders use RC4 keys stored inside the binary to encrypt and decrypt communications to and from the command and control server. These keys change with every new campaign, so roughly every 24 hours, and the old keys become useless. And if you've ever looked at Dridex, you'll know that there's that initial sleep period where it will constantly loop around for about 10 minutes or something to evade sandbox detection. So it will basically do nothing for 10 minutes before it gets to the actual good stuff. And so you're better off extracting things automatically and statically rather than doing it dynamically and putting it into a sandbox. So without having too much theory behind it, let's actually have a go at writing our own config extractor for the first malware sample we looked at in the last video. Okay, so config extraction. So I have the iced-id loader open in IDA over here, and I have my Python script over here that we're going to be using to essentially extract the config from the iced-id loader. So if you remember from the static analysis, we saw that it was using RC4 decryption to decrypt the configuration stored in the data section here, and the first 8 bytes of the data section was used as the RC4 key, and then the rest of it was just data. So one possibility we have when it comes to writing an extraction script is we could use something like regex to figure out all the calls to the address of RC4 decrypt. But in this case, we can see that it's hard-coded, it's pointing directly to the data section. As we haven't got any other samples at the moment, we don't know if the offset will change or if it will stay the same. So let's go ahead and play it safe and say it will stay the same for now. And if it turns out that the configuration isn't at a standard address in the data section, then we can go ahead and write some regular expressions to locate it. So first things first, what we want to do is actually write a script that will go ahead and decrypt the configuration. So before we even work out how to extract it from the binary, we need to go ahead and figure out if we can even decrypt it. So I have my main function over here. And what we're going to want to do is we're going to want an RC4 decryption function. So if we do def RC4 decrypt, and we have the arguments be the key and the data. So rather than write our own implementation of RC4, we can actually use a pretty neat module called RC4. So if you do pip install RC4, I think I might have already got it installed, I'm not too sure. And yep, so if you install RC4 through pip, I don't believe it's a standard module. And then if we go over to the Python script over here, and we do from RC4 import RC4. Now in our RC4 decrypt function, so now all we need to do is if we type in cipher equals RC4, and then put our key as an argument. The RC4 value here is basically a class object inside of the module. So if we pass the key to it, we can now go ahead and simply do decrypted is equal to cipher.decrypt, and we pass in the data there. So now we can go ahead and return decrypted. And this is basically our short and sweet RC4 decryption function. Now we want to go ahead and test this out. So if we now take the data as a raw input and and just add this string in here. So raw input config. So now we will manually input the binary data, but as we don't want to have any issues with copying it out, we're probably going to want to copy it as hex. So let's go ahead and put a binasci.unhexlify, jump to the end of the string, that extra bracket. So now we have the data in the Python script. We want to go ahead now and sort of extract the key from the data. So we know the first 8 bytes, I believe, are used for the RC4 decryption key. So if we now type in key equals data and then 8 like that. So this should take the first 8 bytes. And now if we do data equals data and then 8 and then a colon, this should take everything after the key. So we should now be able to pass it into the RC4 decrypt function, pass in the key, data, and then we want to go ahead and simply just print the return value. Print. So this is the basic script we've got. We just need to import binasci. So now we want to go ahead and extract the configuration. So it's 584 bytes or 0x248. So if we now go to this offset here, we need to copy the data from 403 and then 3 zeros up to 403248. So let's select that and scroll down until we get to 248, and here we are. So now if we press shift and select all this data and then shift and E, it will allow us to copy it all out as binary data. So let's select all of that, copy it out, and let's jump to our terminal window. So if we do Python and then extract.py, hit enter, and then we want to paste our config in. So we've pasted all of the data we copied from IDA, we hit enter, and you can see that we now have the URLs inside of the config. We've got the index.php and then this initial value here. So now we know that the basic config decryption works. We can go ahead and start work on extraction. So to do that, we're going to be using a module called PE file. So let's import PE file. And let's see if I've actually got it installed. So pip install PE file. Yep, I've already got PE file installed. So we're going to want a config extract function now. So config extract in the file name. And now if we change data here to the file name and raw underscore input, change that to file name. We no longer need binasci, so we can remove that. And if we now pass the file name into config extract and store the return value in data. So now the main function is set up as it should be. Let's remove that I there. So we put in the file name of the loader, it will extract the config, will extract the key from the data and then store the correct data inside of data. Then we RC4 decrypt it. So let's now move on to finishing the config extract function. So instead of doing f equals open and then passing the file name in like that, we can actually use PE file to handle it for us. So PE equals PE file.pe and then file name. So if we now just print PE and return none, we don't really want to call the decryption function. So let's just comment that out. So now if we go back to the terminal, do Python extract.py, the file name is dumped loader.bin. We have all this data which has been extracted with PE file, so it passes pretty much the whole binary for us, which is really good. So it'll tell us the DOS header, the NT headers, the file header, optional header. So we're most interested in the sections, which can be found in the PE sections. So just underneath the optional header, if we scroll down, here we've got the PE sections. So we've got .text, .rdata, and then we've got .data. So this will give us information like the name, the physical address, the virtual size, the virtual address, all that stuff. So we basically need to get the sections here. So we need to loop through the different sections and check if the name matches the string .data. And then if it does match, we want to get the virtual address of the data section, and then we can go ahead and extract pretty much the entire config like that. What we can go ahead and do is print pe.sections, which I believe is the correct function. So now if we call our script, we pass in dumped loader.bin, enter, run that, and as we can see, it's actually a list, not a function. So let's remove those brackets there, run it once more, dumped loader.bin. We can see that it's actually stored as a list. And so because we know this, we can simply change this to a for loop for section in pe.sections, print section. Now clear this out, dumped loader.bin. It will just print out all the sections. So now I believe if we go ahead and put name in there, we can clear that out and run this one more time. It should only print out the names of the sections. And yep, it only prints out the names. So now we have the different section names printed out. We can change this to an if statement. So if section name is equal to .data, then we want to go ahead and print, I think it was a section dot virtual address. So let's run this again, dumped loader.bin. And interestingly, it doesn't print anything. So that means there could be some null bytes on the end of this. And while we could use something like bin ASCII, let's go ahead and change it to if.data in section.name. We should be able to run it again. Hopefully this should work, dumped loader.bin. And we now have the virtual address of the data section stored in decimal format. So now we have the correct section and we're getting the information about it. We could go ahead and use this virtual address and then pass it to a function that opens a file, reads it from that offset and everything. Or we could just simply remove this and put in the inbuilt function get data. And hopefully what should happen is it should print all the data inside of the .data section. So now if we run dumped loader.bin, it prints out all of this data here, which obviously because it's raw data, I'm not entirely sure exactly if it matches the hex output we saw earlier, but we can go ahead and return this. Let's comment out this return none. We then uncomment the key and the data and the RC4 decrypt. Let's run this once more, dumped loader.bin. And as you can see, we now have the entirety of the config that's decrypted. And obviously because we're not mentioning anything about the size, it will just try and decrypt the rest of the data, which isn't valid. So because if we were to output this to a emulator or something, we don't really need the extra data. Let's manually change the size of it. So if we now go to IDA, we can see this is the size, so 584 bytes. So now if we do data is from offset 8 to offset 592. So that's 8 bytes after the actual size here, just because we're stating that the config starts 8 bytes after the data section, and we just need to do that so Python can correctly output. Otherwise the config length would be 8 bytes less. So now if we go back to the terminal window, clear that out and run it again, dumped loader.bin, we now have the decrypted configuration. So that's pretty much how we can go about extracting the config from the ICED loader. And what we're going to do in the next part is we're going to actually develop our own emulator for it. However, first we've got to develop a config extractor for the second loader we looked at. So let's go ahead and do that now. So now we've written a config extractor for the first sample we looked at. Let's actually write another one for the second sample we looked at in the last video as well. Okay, so config extraction. So this is the function that decrypts our config, and this is the config in memory here. So let's view that. So the configuration is stored 4 bytes into the data section from the looks of it. This obviously could change, in which case you would use regex to, figure out the location, which shouldn't be too hard considering there is a 20 byte lowercase character string inside the data section. And so you could probably just perform a regex on that and then get the 750 bytes beforehand. So knowing that it is at the very start of the data section, what we can go ahead and do is use PE file to locate the data section, extract that, and then take the data from 4 bytes on until we reach a 20-byte character string. So we could use regex for this, but as I haven't planned out how we're going to write this script, we might end up not using it. We'll have to see what the results are. So let's jump over to the IDE over here. I've actually gone ahead and copied the zloader.bin into the project directory. Hopefully Windows Defender doesn't decide to delete it. So I've also installed PE file and RC4. So if we do import PE file and from RC4 import RC4. So first things first, let's get our quick RC4 decrypt function out of the way. So RC4 decrypt, key data, and then we do cipher equals RC4 and then pass in the key like that. Then we just do cipher.decrypt data, and we can go ahead and return this. So that's the basic RC4 decrypt function. There's going to be a few underlines here because PyCharm likes to pretty much correct everything if it's not to standard, but in this case, you know, we're going to ignore how it should look and just go for practicality over looks. So we've got our RC4 decrypt function. Now we need to go ahead and extract the config from the binary. So let's create our main function. So def main, then if underscore underscore name is equal to underscore underscore main. Then we want to execute main, and main will be responsible for firstly getting the file name equals raw underscore input, and we're going to set the prompt as zloader binary. This will then be passed into a function that will retrieve config, and this will take file name as a parameter. So the retrieve config will return the encrypted config, and what we will do then is we'll have the RC4 decrypt function take the encrypted config and then the key, which will also be returned by the retrieve config function. So let's set that as key, and now we have the encrypted config and the key being returned, and then decrypting the actual config, we actually need to swap around the key here. So that's going to be argument 1. So let's set that there. Now RC4 decrypt will return the decrypted data. So we have decrypted config is equal to that. And we simply go ahead and print decrypted config. So now we have a method of getting the file name, a method of retrieving the config, and a method of decrypting it. So all we need to do now is fill in the retrieve config function, and we're pretty much ready to go. So let's define that function here. So def retrieve config. This will take the file name. And now what we do is, first things first, we're going to want to pass it into PE file. So PE equals PE file.pe. Pass in the file name. So this will open it for reading. Let's lowercase that. So now what we can go ahead and do is, let's say we will loop through all the sections of the PE file and see if we can find the data section. So for section in PE.sections, let's print section to begin with to make sure that we're getting the right data. Comment that out, and let's simply run this. So Python config extract.py. We want the binary zloader.bin, and it seems Windows Defender has decided to delete the file. So I've gone ahead and copied the file back into the current directory. So let's do dir, and we can see that zloader.bin is there. Now we run our extractor and we type in zloader.bin. As you can see, we have now got a list of the sections. So we've got reloc, resource, .data, and rdata, and then we have .text. So now what we do is we go for each section in PE sections. We want to do if .data in section, then we want to go ahead and get that section data. So data section is equal to section dot get data, I believe. Now with that, we can go ahead and print data section just to make sure we've got the right thing. Let's go ahead and clear the terminal, run this once more, zloader.bin. For some reason it's not iteratable. Yeah, that's why. So we need to add a .name on the end there. Clear this out, run it again, zloader.bin, and it seems there's no attribute get data. So there's a underscore between get data here, and if we run it once more, zloader.bin, we have the entirety of the data section. So there's a lot of bytes here. Somewhere we might be able to locate our lowercase string. It doesn't seem to look like it at the moment, but that's fine. We don't really need to worry about that right now. Let's clear that out, make it a bit cleaner. So now we've got the data section. We can break out of this loop. Obviously you'd put in some error handling here. So if data section was null and it didn't locate a data section, then it wouldn't execute this part. But in this case, we're going for an initial config extraction rather than a full-on production extractor. So now we have the data. We can go ahead and extract the important data. So we don't need the first few bytes. So data section equals data section. Skip the first 4 bytes. Now we have the full data section. So if we print data section and only print the first 780 bytes, which is the config plus, I believe, the 20-byte string, this should print out everything that we need, essentially. So let's run it once more, zloader.bin. It doesn't really show us much, so let's import binasky. We can go ahead and print binasky.hexlify, close brackets. So going ahead and running this now should hopefully output some useful data. So zloader.bin. And interestingly, it doesn't seem to give us the correct data, which is quite strange. We've requested the data section and we've requested to retrieve that specific data, but it doesn't seem to have given us what we wanted. So it looks like we may have to go ahead and use regular expressions as well. Let's go ahead and print the whole data section to see if there's any useful information in there that we can find. And it doesn't really look like it's all obviously hexlified. So I think this data here might be our config because of the amount of bytes there are. And then we have all of these zeros here. What we can actually try and do here is we can pass this data section into a regular expression function that will go ahead and locate our key. So let's clear that out. We want to jump back to our IDA virtual machine and we want to scroll down until we have that 20-byte character key. So we're going to have to do some testing when it comes to writing some regular expressions. So here's our 20-byte key here. Let's copy that out, jump back over to our script. Let's paste this in just here. And now we're going to go to a regular expression testing site. So let's go ahead and jump over to that now. Here we are using a site called regexer, and we can go ahead and delete this text data here, paste in our key. So what we're looking for is we're trying to write a regular expression to match this key here. So they've given us this basic expression here, which tells us that it matches a character in the range A to Z, and it's case sensitive. So we're going to be using this format, and in brackets, groups contain multiple tokens together. It's got a word, matches any word character, match one or more of the preceding tokens, and then we've got a close. So what we're going for here is, let's select all of that. We're going for A to Z, close that. So as you can see, it matches everything, although specifically we're looking for a 20-byte string. So I believe, if I can remember correctly, all we need to do is add this 20 in here. And as you can see, it will only select the string and the entire string if it's 20 bytes. If we take away one of the characters here, it won't select it because it's 19 bytes. If we add a character and then add another character, it will only select the 20-byte key. So this is obviously a very basic implementation of regex. Like, there's a lot more stuff to it. In this case, we're only looking for a 20-byte character key, all lowercase. When it comes to extracting other configs that have, specific byte patterns you need to adhere to, or specific values that may or may not be there, then you look at wildcards and everything. In this case, this is our pattern here to locate it. So we copy that out, jump back to our script here, and now we need to add a function called def locate config key, and then we want the data. So this will use the pattern that. So now we need to go ahead and import RE. So regular expressions are quite difficult when it comes to working with them in Python. So one of the best sources you can go to when it comes to learning about this stuff is the Python docs themselves. So what we're looking for here is we're looking for the functionality of locating specific strings. So we need to essentially execute the regular expression. So if we search for find, it'll come up with quite a lot of cross-references. So we've got the re.search, so scan through string looking for first location where the regular expression pattern produces a match, and return a corresponding match object instance. Return none if no position in the string matches the pattern. Note this is different from finding a zero length match at some point in the string. I think we're going to be using the function re.search, so let's go ahead and put in match object equals re.search. So we take a pattern here, so pattern, we take the string data, and there was one other value in there, flag, so we don't really care about the flags in this case. So we have match object is equal to re.search pattern data. Now if we print match object just to see what the output is, and let's go ahead and pass our data section into this locate config key, the data section. Now let's run the config extractor, zloader.bin. We have a match object. So if you remember, it says that it will return a none if no position in the string matches. So it has definitely found a key inside of it. So regex is extremely useful for when you're dealing with unpacked samples that haven't been rebased properly, or offsets are quite different, and so you have to go ahead and perform a search on the entire data section itself. So we've got this match object here, and we can go back to the docs and see what this match object instance is. So we've got expand, group, groups, group dict, start, and end. So we're interested in the start and the end value, which will basically give us the entire string. So if we print match object.start, it will give us the offset, I believe, of our config key. So if we run this again and we type in zloader.bin, it will give us the offset inside of our data of the encryption key. So we can go ahead and use that as an offset inside of the data variable. So like that. And then we have a match object.end. Now we go ahead and clear that out, run it again, and we put in zloader.bin. So now what should happen is it should print our entire 20-byte string. Let's run that. And it has located a string, but it isn't actually ours, which is quite interesting. So what I'm guessing is we may have gotten the incorrect section or something here, or it has managed to locate another string that isn't the valid one. Let's go ahead and take a fairly different approach to this. Let's use hxd quickly to locate where this string actually is. So now we want to copy that string out, search, and then we want to do a search. So search, find, search for, and it's going to be a text string. Interestingly, it cannot locate it inside the binary. So that is very interesting that it can't seem to locate it. I have a feeling we could be dealing with the wrong thing here. So I've now moved around the files. Let's go ahead and run our config extractor. So zloader.bin. And as you can see, it has now returned our correct string. So that was probably why we couldn't locate it properly in the last option we had, but you know, these things happen. So at least you've got to see how we can use regex to locate it. So now we have the location of the key. What we're going to go ahead and do is we're going to put key is equal to data, and then match object.start, match object.end, And now we need to basically extract the config from the information we've got now. So if you remember when we looked at the binary itself, in IDA we saw that the value 751 was pushed as an integer as a size of the config to extract. So let's assume that that value stays the same and it never changes, which as far as I'm aware, it doesn't seem to change in each sample. So using that knowledge, we can go ahead and do config is equal to data and then match object dot start minus 751 to match object dot start. So this will get all the data 751 bytes before the match object dot start, so before the key. So now we have the config, so print bin ASCII dot hexlify config. We jump over to the terminal, run the script zloader.bin. It will now output our hexlified config here. So let's jump to IDA quickly. Scroll down to see where the key is again. Actually, I should have it in history. There it is. So the last value before the key is 8B. And now jumping back to our script, we can see 8B is the last value here. So that means we have the full config. We can go ahead and simply return the config and the key, uncomment this line here and that line there. We now will decrypt it and everything, so clear this out, run again, and hopefully we should have the decrypted config. And it looks like none type object is not iterable. So there's an issue with, yeah, that's why. So we return from this function, but we don't return from this function. So let's add a return here, clear this out, run it once more, zloader.bin. And here we go, we have the URLs inside of the zloader config. So we've got 2503, we've got the first URL, the second URL, and then some additional data. So that pretty much wraps up the config extraction phase. So we've seen how we can use regular expressions, while basic, still pretty useful in locating keys. So even if they change the offset of the config, we can simply search for the pattern again, locate the key very easily. We've used PE file to extract this and pass it into the regular expression function, and then we've gone ahead and decrypted it. So what we're going to go ahead and do now is having a brief look at the communications. So we're going to look again at the packet structure, and we're going to have a look at how we can create structures based on the bin storage. So look at the open source code, try and replicate it in IDA so it's easier to analyze, as well as set our own symbolic constants for assigning to different values. So let's go ahead and get into that now. So now we have two config extractors for two malware families. Let's have a look at communication emulation. So with the latest list of command and control servers and encryption keys in hand, it's time to emulate the communications. This requires knowledge of the communications protocol plus any algorithms used for encryption. Does it use HTTP, HTTPS, FTP, or raw sockets? And is there any compression, encryption, or obfuscation? So being able to interact with the command and control servers to get the latest payload allows us to track the malware family and potential groups using it. And the stuff we're able to track ranges from changes in the code base, potential links between command and control addresses, or just tactics, techniques, and procedures attributed to that specific group. So the possibilities are endless. Once we emulate the communications, we can write packet capture parsers, snort rules, Yara rules, command and control panel locators, or even a fully automated tracking system. So enough of the theory, let's actually go ahead and write a communications emulator for our first malware sample that we wrote the config extractor for. Okay, so now we're going to go ahead and develop our communications emulator for iced-id. So I've gone and cleaned up our extractor a bit. So I've put it into a class config extract, and then we call that and extract it. So it all works the same. The code's just a bit neater. So if we go ahead and run it, dump loader.bin, you can see it extracts the config. So at this point, what we do is we'd go ahead and pass the config. So we'd get the different values that we needed and then extract the URLs from this blob of data. And then we pass it into our communications emulator. So I won't do the parsing in this bit, so I'll leave that up to you to do. but we will have a look at setting up our communications emulator. So to start off with, let's create a new class, name it Emulator, then def init, put self in there. And at this point, I'm not entirely sure what we should pass to it. It could be a URL. So let's go ahead and put in URL here. And then we do self URL equals URL. So looking back at when we analyzed the main communications routine, I only believe there was really just the communications going on. It wouldn't do anything else. There would be no additional routine. So in that case, we can go ahead and create one function called send request, which will send the request to the command and control server, and then the response will be decrypted. Obviously, the command and control servers are down, but we do know that it is going to be in the format of a PNG file. In our full analysis of iced-id later on, we're going to look at how it parses those PNGs and decrypts it. So for this, we're just going to look at how to send the request and what the response is going to be like. So we've got this send request function, and we're going to be using the requests module for this. So if you haven't got it installed, just do pip install requests. And as you can see, we've already got it installed. So let's jump to our machine with IDA on it and just revisit the communications and see how we should structure our send request bit. So here's the communications function. So we have this one string here. So let's copy out this placeholder and put it into here. So aside from our send request function, we're going to define a function that will build our packet to send. So build the URL basically, as there's no additional data. So build URL self, and then for now let's leave it just like that. There's no arguments to it, and our placeholder string is going to be this. So we know the data that is going to be passed into this string. So we've got the value 1, we've got this D word here, which points to the configuration. I believe that's the very start of the config. So it would be the first D word inside the config. So in that case, let us go ahead and use the binASCII module. So import binASCII, and let's hexlify the output of this. So binASCII.hexlify. And now we want to run the config extractor again. Hopefully, okay, we need to fill in, we need to sort out this stuff. So let's just change this to a parse. And now we run it again. File name dumped loader.bin. So the first D word in the config is FB333D1E. So let's go ahead and copy that out and just store that as a comment here for later. Okay. So then it will have the return value of the RDTSC, so the retrieval of the timestamp. So we have the value 1, then we have the config value, then we have a timestamp, and then we have the PC info retrieved from the possible anti-VM function. So once this gets put into URL string, it's going to be converted to a wide string from the looks of it and stored in v17. And the URL is also stored as a wide string inside of the command and control URL. And then we have the port here. So what we're going to do is we're going to figure out the structure of the PC info string. So let's jump into the possible anti-VM, scroll down, and we have this formatting string here. So let's copy that out, and over to our Sublime text, we have the PC info placeholder equals, and then paste that in. So this contains v25, v24, v23, 22, 21, 20, and then EAX. So we could statically work this out, but it's probably just quicker to get it done in a debugger. So let's go ahead and jump over to the debugger here and find our way to the communications routine. The address of the function is 401224. Obviously, these are two different offsets in here, so we can't really directly do it, but let's try and find the photo.png string, which is here. We concatenate the strings here. Scroll down, here's the call to the config decrypt. It'll check if a file exists, and if it doesn't, it will jump down to here. And here we've got the communications routine. We've got the retrieval of the timestamp, so let's put a breakpoint at the very start and run to it. So now let's step through this function, step into the anti-VM function, and we're mainly interested in the call to wsprintf. So let's put a breakpoint there and run. So now we've hit the call to wsprintf. We can follow dword and dump, and this looks like where it's going to be stored. Is this another dword? No. Okay. So I think this is where it's going to be stored, the output of the string. So now if we step over that, we can see that the entire string has been formatted. So it's a bunch of zeros followed by an FF, followed by a 4, and then a few more zeros, and then a 6. So we know that this value after the 2 Fs is something to do with the processor and directly corresponds to VirtualBox. So in that case, we're going to want to probably change that for when we actually begin to emulate it, because it's most likely the case that they're checking what this value is on the back end, and if they detect it's VirtualBox or VMware, then they'll probably not send you the right response back. So now we hit the return. We've got this string here, so we've got 10 zeros. So let's jump to our emulator over here. So PC info, we've got 10 zeros, then we have 2 Fs, and followed by the processor information. So for us it's a 4 followed by 6 zeros, so put that in there, and then we have a 6 at the end. So now once we have got this string, it will retrieve the timestamp once again, and the first part of the timestamp is stored inside of EAX. And so in this case, let's use the timestamp stored inside of EAX. So it's 3A298D54, I think. Yep, that looks correct. So then we push these values to a call to wsprintf, follow dword in dump. This is where the output string is going to be. And now let's check the values that are pushed. So we've got the 1, we've got this value here, the 1ED, which is the first value in the config. Our config is just flipped, so this is actually the wrong way. So it should be 1E3D 33FB. Then we have the timestamp, which we've got here, the 3A, and then we have the string that we've just generated. That's the several zeros, FF, and then the 4, followed by 6 zeros, and then the 6. And that seems to pretty much be it. So now we have all this information here. We can go ahead and hopefully fill in the placeholder. So placeholder equals placeholder. And then we have the values here. So we've got the value 1. We have the config val equals this. Let's copy that, paste that in. Then we want to change it into a hex string. Okay, now we want to copy these out, and basically we're turning it into a hex format, although we might need to change it to an integer. Not sure at this point. We'll need to go ahead and see if this works first. So we've got the timestamp is equal to this string here. Once again, converting it to a hex format, although I'm pretty sure this will be stored as an integer. So then we have the PC info, which is equal to, this is a string in this case. So it is 10 zeros, so let's add the 10 zeros, and then 2 Fs followed by a 4, and then 6 zeros, and then a 6. So because we're not worrying about the PC info placeholder at this point, if we were going to write a mass emulator for most iStudy samples, we'd probably have something in place to do that. Otherwise, we'll just comment that out. And let's put in our values here. So it's the config val, followed by the timestamp, followed by the PC info. Now if we go ahead and print the placeholder to see what the output we get is, and then we need to now go ahead and let's remove this bin ASCII thing here. So now we've pretty much almost finished our draft of our build URL function. Let's go ahead and get the URL we're going to be using. So dumped loader.bin. Now we can go ahead and initialize our emulator class. So emulate equals emulator, and then we want to pass in our URL. So let's use this first URL here. Paste that in, and then we call emulate.build URL. So this should hopefully print out our placeholder. So let's run this again, dumped loader.bin. And as you can see, it does require a number. So in that case, we can go ahead and change this to an integer. So 0x like that, and then change this timestamp to an integer as well. Okay, and add a 0x at the start. Let's run it again, dumped loader.bin. And here we have our full generated string. So now we have that, let's go ahead and see what the debugger outputs. If we F8 over that, we have the string here. If we follow D1 dump, we've got 01, 1E, 3D, 33. So it looks pretty much identical at this point. So you should always check your output of your packet builder alongside the debugger output just to make sure that your values are correct. Although in cases where there's anti-analysis methods, you'll probably want to have a different value compared to the debugger, because the debugger will obviously be running inside of a VM, and obviously the program's running inside of a debugger. If it sets a value as 1 for running in a debugger, you'll want to set that as a 0. So we've now got our completed packet to send to the command and control server. All we need to do now is prepend the URL to the start of this, and then make a GET request, I believe, to the server. So if we go to comms again, scroll down, we've got check C2, and yep, it's a GET request. So we can use the requests module for this. But first we need to prepend our URL. So then if we do packet to send is equal to self.url plus the placeholder, and then we want to return packet to send, and now we print it here. Let's run this once more, dumped loader.bin. We now have the full string we're going to send to the server, and all we need to do now is add in our send request here. So what we do is we do r equals requests.get, and URL is equal to the argument we're going to add in here, which is the data. So URL is equal to data. I don't believe there are any headers added here, so let's just jump back. Doesn't look like there's anything added. No specific headers that need to be used. So in that case, we can go ahead and ignore that. So we do the r equals request.get, and all we need to do now is add in our emulate.sendRequest with our data to send. Then data to send is equal to emulate.build URL. So let's run again, dumped loader.bin, and we now need to prepend a HTTP, but it does send over port 443, so it's highly likely to use HTTPS. Let's change this to HTTPS and run the thing again, dumped loader.bin. It will try to connect, but because the command and control servers are down, it shouldn't respond with anything, and it will take quite a while. But this is essentially the simple method of sending a GET request to the command and control server. You can add in specific headers alongside this or any other data. So as you can see, it didn't connect properly because the server didn't respond. But what you do now is you'd have the variable r, which you could use. You could print r.content, which is the information stored inside of that. So if we went ahead and did that for something like Google, you should be able to see how it will output the data. So google.com, dumped loader.bin. We can see that the data printed out, the r.content, is the HTML of the code. So in the case of IcedID, this would be the PNG file that had the encrypted data inside of it. So yeah, that pretty much sums up how you can utilize the debugger and IDA to develop a basic emulator for the loaders. In the next part, we're going to look at the structure of the loader, but we're not going to develop an emulator like this. I'll leave that up to you as a challenge. although the sample I've picked, I believe, is fairly easy to develop one for because it uses a lot of open source code. So yeah, that pretty much wraps up the basic analysis of the IcedID loader. So we will be looking at IcedID once again later on in the full analysis, though less on the emulation really and more on the functionality and everything inside of it. But yeah, thanks for watching, and let's move on to looking at emulating the next loader. Now we've written a communications emulator for the first malware family. Let's go ahead and write one for the second family we looked at. Now we're going to have a look at how to basically replicate structs inside of IDA. So if we go ahead and we've got v11 here, which is equal to our bin storage. If we right click it, you'll see that it says convert to struct. Now there's no actual structs declared inside of IDA. A lot of the time it will recognize structures when it comes to stuff like Windows structures, so actually defined stuff. But in cases of Zeus, it's not really a defined thing anywhere other than the source codes. So we will need to go ahead and basically set up our own struct inside of IDA so it can recognize it. So luckily for us, we do have the open source code of it, which will allow us to make this a lot easier. So we have item ID, we've got item flags and item real size. Item in this case is equal to p plus p size. So this is basically the base address of the storage plus the size of it. So nothing really too difficult. We also have the bin storage.h over here, which will tell us the structure of this item function. So we've got dword ID, dword flags, dword size, and then dword real size. We've also got this storage structure here. So random data, size, flags, count, MD5 hash. But in this case, we want to focus on the item structure. So if we go to structures now, we see there's a few options for us. So create structure member, rename structure, and delete structure. So we want to go ahead and insert one. So let's insert. Structure name is going to be called item. And we're going to click OK. If we right click this and put in data there, it will create our first field. So we want to have each field be a dword, as the header file tells us each section is a dword. So that's 4 dwords, so it's 16 bytes in length. So if we select this as a dword, and then we want to go ahead and expand struct type by 12, I believe. Rename this because otherwise we'll have an issue. So let's select the first one. So that's the first dword, second dword, third dword, and then we've got the fourth. So the first one is equal to ID and then flags, size, real size. So ID, flags, size, and then real size. Now if we jump back to the pseudocode, just refresh this so everything's up to date. We know that v11 is equal to our item structure. So if we right click, convert to struct, select item, it will now pretty much fill in everything for us. So item ID is equal to ID, item flags is equal to v7, which is linked to flags up here, so it's most likely going to be equal to it. And then real size is equal to size. So that's pretty simple to do, nothing too difficult. We see v11 is equal to v10 here, v10 is equal to empty memory plus v16. We could go ahead and basically do structures for all of these things and make it a lot easier to analyze, but I will leave that up to you as it can get quite monotonous going through adding structures and everything. This is a great sample to play with as it allows you to see how obfuscation can be added to something as open source as Zeus to make it even harder to analyze. Although if you do get stuck, a lot of the code is available on GitHub. So you can easily go, oh, actually I know what this does now because I can cross-reference between GitHub and IDA. So now we've figured out how to create our own structures. Let's have a look at adding enums. So back out of this function, we can see that these values here, 10029, 10002, these all have corresponding values, but because it's not like inside of kernel 32 or something, it's not a standard, it won't be inside of IDA. So we'll have to manually search up what all of these mean and then simply add a comment next to it like, okay, this is the bot ID and so on. However, if we use enums, we don't actually need to use this. We can simply go to the regular graph view, right click this value here, and we have use standard symbolic constant. Obviously there's nothing there yet, but eventually there should be our values here. So we can go ahead and select it and it will rename it. So let's go ahead and start with this one here, this 10002, which has already been defined. I cannot remember exactly what it was, but we can go ahead and search it up in the GitHub repository. So we have, thankfully, a config.h here. So 10002 is equal to sbcid botnet. So let's copy that out. We can jump over to enums. So what we're going to go ahead and do here is similar to the structures. We need to add a enumeration type first, and then we can go ahead and create a symbolic constant. So if we click insert, we've got enum2 here, but we want to name it Zeus enums. So Zeus enums. Now right click this, add enum member. We can add the sbcid botnet, and the value is going to be 10002. If we click OK, we have now mapped this value to the value 0x2712, which is equal to the 1 followed by 3 zeros followed by a 2. We can go ahead and do the same for the bot version here. So if we go ahead and right click, add enum member, bot version, this is equal to 2713. Yep, it's one after. And it seems that it's because there's a space on the end. It doesn't like that. If we click OK now, it has now successfully added it to our list of enums. So now if we jump to the pseudocode, refresh the function, right click this, we can see enum is here. So M is the shortcut, click that, and it recognizes it as sbcid underscore botnet. Now if we want to do it from the graph view, we simply have to right click, symbolic constant, sbcid underscore botnet, and it will automatically select it for us in the graph mode and also in the pseudocode. So that pretty much sums up this part of the chapter. Obviously I wanted to leave the analysis of the communications as sort of a challenge because it's a difficult thing to analyze, but it's not too difficult as there's a lot of code open for you to analyze and figure out how to implement your own bin storage stuff in Python. And it's a great learning experience as there's not a lot of stuff out there written about zloader. So you are sort of in some way forced to analyze it on your own. Although with the information I've given you and the links I'll leave, you should be able to come up with something pretty interesting. So you see this value here as well. These are also enums that we can use. So these are the flags. So you'd go ahead and create a new enumeration type called Zeus flags. Then you'd create the different flags. Now everything's already inside of the GitHub for you if you want to go ahead and take a look at that. But yeah, that pretty much wraps up our analysis on the second loader, which is obviously zloader. So this has been a very long chapter, although hopefully you've learned quite a lot from it as we go quite into depth in some of these samples and we learn a few new tricks like structures and enums. But yeah, that pretty much wraps up the packet structure, communications related stuff. Later on in the full analysis, we'll be writing a string decryptor for IDA, but it's for a different family. It can be altered and used for this, which will allow you to analyze the sample even faster. So think of this like a starting point where you can follow the whole course through and then take all the information you've learned from the course and apply it to this one sample to hopefully figure out how everything works. And yeah, that's pretty much it. So yeah, as I was saying, hopefully you've learned something from analyzing these two loaders, and yeah, it's time to move on. So to recap in this episode, we looked at configuration extractors, why we need them, why they're useful, as well as writing two config extractors for two malware families. We then looked at communications emulation and why it's useful, what possibilities you can use with it once you've got it working. And from there, we wrote two communications emulators for the two families we previously looked at. So that pretty much wraps up this chapter in the course on initial stages. In the next part of the course, we're going to be looking at and focusing on evasion. So we're going to be looking at anti-analysis methods, persistence methods, injection methods, and all that stuff that's related to loaders. So loaders typically will inject the follow-up payload into memory somewhere or into another process, or perhaps it'll even run it on disk, which is unlikely. But understanding injection and anti-analysis methods is extremely important and critical when it comes to analyzing sophisticated malware families, as Anything higher than your regular script kiddie keylogger will most likely include some form of anti-analysis that isn't is debugger present. So we're going to go ahead and look at that in the next chapter. But yeah, that brings us into this chapter of the course. So I hope you found something useful in it, and I hope you learned something from it. And at least now you've got 2 config extractors that you may not have had before. So yeah, thanks for watching, and I'll see you in the next chapter.